Welcome again. This lesson entitled Introduction to Embedded Systems. In the previous lesson, we defined machine learning and capabilities. Now it's time to discuss with you what are embedded systems, their significance, the difference between data centers and endpoints, and a brief introduction to microcontrollers, the heart of embedded systems. Embedded systems are specialized computing devices that integrate hardware and software to perform specific functions, transform modern technology, in which they power a wide array of devices, from consumer electronics to industrial machinery, enhancing functionality and enabling seamless automation. The design consideration of embedded systems involve careful attention to power consumption, real-time operation, and physical constraints is essential for the seamless and integration of embedded systems. What are the significance of embedded systems? Now I will discuss with you two of embedded systems' significance: enhanced functionality and impact on innovation. Enhanced functionality. So, embedded systems enhance the functionality of devices, enabling advanced features and seamless automation, contributing to operational efficiency and precision. Impact on innovation. The prevalence of embedded systems derive innovation, transforming industries and shaping the future of technology, fostering support for social equality and civil rights. Now it's your turn to answer the following question. In the previous video, I mentioned that one of the limitations of machine learning is the lack of data. So, what companies are doing? They are taking all these computers and jam-packing them into data centers that are all just being dedicated in order to provide machine learning capabilities. Today, these data centers are so big that they take up a big block. Now, what's really interesting is that in order to be able to provide that capability, companies like Google are building tensor processing units, or companies like NVIDIA are building graphics processing units, GPU. Both of these kind of architectures, these computing systems are capable of running machine learning extremely fast. Bigger is not always better. I will tell you, think about it. When you have a large data center, what are the limitations? You cannot have immediate interactivity. You cannot carry a big data center in your pocket to quickly take a picture, right? Because when you take a picture, you want the system to respond swiftly. But if it has to send data to another computer elsewhere, it will be slow, correct? But imagine if you could incorporate all that computing power into your phone. Why? Because doing so would enable various applications to be much more responsive and interactive. For instance, when you say, "Okay, Google," the device could instantly wake up, allowing you to schedule a calendar appointment or perform other tasks. Okay. When comparing a large computing system to a small device, what are the major differences? If I cram numerous big computers into a massive block of cement, it consumes a significant amount of power. However, with smartphone, power consumption is very, very low because it's a small device powered by a battery. In terms of bandwidth, a data center can process a vast amount of data efficiently because all the machines are closely packed together. This proximity enables fast movement of data, facilitating high-performance computing. However, on a smartphone, there is a less assurance regarding bandwidth, the capability to transfer data to or from the device. In a data center, accessing it entails high latency, since it's located far away. Sending data to the center and receiving a response take time. despite the substantial computational power available there. On the other hand, conducting machine learning tasks on a phone is faster because the device is readily available in your hand. It can process tasks swiftly without the need to transfer large amount of data back and forth. So now, take your time to complete the exercise. Now, this is where things get really interesting because we want to move from data centers to smartphones. But the reason we want to move that is because there is a lot of interactivity and a lot of interesting real-time kind of behavior pattern that we can exercise with machine learning. We can get even more as we make the devices completely pervasive in our homes. Think about a phone. A phone is only there wherever you are. These are so many times I forget where I put my phone. But if I have a smart device, in fact, I have about 7 smart devices in houses, let alone my watches. These small little devices are more and more becoming pervasive throughout us. And we want all of these devices to be intelligent. Right now, I want you to realize the many options available, the types of devices that can all possess intelligence. If they are capable of being intelligent, it implies they are swiftly processing data locally. So instead of constantly sending it elsewhere and waiting for it to return, which consumes a lot of power and drains energy, so processing data locally is much more efficient. Consider your smartwatch, which conducts machine learning directly on the device. You could also have intelligent AirPods. Sure, let's break it down. When we discuss the challenges in the embedded realm, we are essentially talking about the difficulties that come up in the field of small computing devices. This understanding helps us figure out how to use machine learning on those devices effectively. Like any system, an embedded system is just like a regular computer. It has parts, such as hardware and software. So, understanding both hardware and software is really important in embedded systems. This helps us figure out how to use them effectively. It also guides us on what changes we might need to make to use machine learning on them. Let's start by looking at hardware. Normally, in any computer system, hardware consists of 3 main parts: computing power, memory, and storage. The computing power is like the brain of the system. It does all the thinking and processing. Memory is where data is stored temporarily, kind of like short memory in our brains. And storage is like a permanent hard disk. Even when the power is turned off, it still keeps your data safe. So, in summary, these 3 parts, computer power, memory, and storage, are the basic elements of any computer system. When you combine these 3 components, there is distinction between a microcontroller and a microprocessor. If you are using a laptop or similar device to watch this video, it likely has a microprocessor doing most of the work. So, a microprocessor is a larger computing engine compared to a microcontroller. A microcontroller is a different type of computing system. So, let me highlight this distinction for you. Consider a laptop. For example, it has a small component called a microprocessor. This microprocessor connects with various other parts of the system. It's just a piece of the larger picture that links everything together. So, you got the microprocessor separately. Then you assemble all the other parts together. That's how you create a typical disk computer, for example. On the flip side, a microcontroller is quite distinct. When you purchase a microcontroller, everything is already put together. So, the processor, memory, and storage are all closely connected. It's like a single solid block of technology. Here is a complete example of a microcontroller. You have got your memory, you have got your RAM, you have got your processor. Everything is fused into one single block that you buy, which is quite unlike when you buy your parts for a regular desktop computer, where you get to cherry pick and choose these different things. And you can build them in any configuration you want. For instance, my laptop has a 32 gigabytes of memory, which is something I custom ordered from Apple. Versus as if you buy the stock laptop, it only comes with 16 gigabytes of memory. So I have this option to configure what kind of system I wanted. But if I am looking at a microcontroller, it's all packaged already into one single thing. So it's either I buy this microcontroller or that configuration of the controller. That's one fundamental difference, major difference I want to keep in mind. Okay, so if I was to kind of generalize this into a critical bullet points, I would say the microprocessor is the heart of a general purpose computing system, where microcontroller is the heart of an embedded system. It's an embedded system versus here. It's a general computer. A microprocessor is just one part, and it interfaces with external component of memory and storage. In the context of a microcontroller, these things are all tightly integrated already into the system. Again, a microprocessor is more meant for general purpose. For general purpose systems like laptops, desktops, and servers, where you get to configure things, while microcontrollers are typically designed for fixed function tasks, like be able to play music on an MP3 player or be able to answer a phone call. That's a very specific task. So microcontrollers generally tend to be quite preset in their functionality, and often a big embedded system might include a phone, which is a very complex embedded system, might include a whole bunch of different microcontrollers that are fused together in order to be able to provide different kinds of functionality. So now, because of flexibility, a microprocessor ends up with very big, in fact, because your laptop is big, you get to put all these parts together. Those interfacing capabilities naturally lend themselves to being big, while a microcontroller is all about making them tiny, because this form factor is small, so you tend to squeeze these things down. So let's put some rough numbers to highlight the difference in microcontrollers. For computing power, a regular microprocessor can run at speed between 1 to 4 gigahertz, while a microcontroller runs much slower, become 1 to 4 hertz. In terms of memory, microprocessor can have megabyte to gigabytes, while microcontrollers usually have only kilobytes of memory. Storage capacity for a microprocessor range from gigabytes to terabytes, whereas microcontrollers typically have kilobytes to megabytes. Regarding power usage, microprocessor consumes 10 of watts, where microcontroller use much less, in range of microwatts to milliwatts. So there is significant difference between the two types, with microcontrollers being much smaller in terms of computing power, memory, storage, and power consumption. Okay, the devices we are discussing are very small. That's the main point here. So what does it mean when you have less memory and low power consumption? It means to consider how complex the task is that we are running. In this course, we will learn about how machine learning interacts with embedded systems and real-world applications. For example, if we want to make smart glasses with a fast real-time processing, a microcontroller might not be the best fit. However, it depends on the specific task at the hand. Also, how much memory do we really need? Microcontrollers vary in memory size from a few kilobytes to hundreds of kilobytes. So, understanding the task and its requirements helps in choosing the right microcontroller. Another important factor is how long the task needs to run and how often. This affects the power consumption. We'll delve deeper into these topics as the program progresses. So, the microcontrollers we have discussing are globally available, but they have limitations and capabilities. However, there are ways to overcome these limitations. Once we understand the constraint scope and limits, we will better appreciate deploying intelligence on these resource-constrained devices. Here are some examples of commercial microcontrollers that can be found in any electronics store or Amazon, like Arduino and our ST boards. These microcontrollers have the capability to be injected to any endpoint and suitable for machine learning deployment. Now it's your turn to answer the question here. Today we have learned about embedded systems, their significance. We learned what are the differences between data centers and endpoints, and also we have now know about microcontrollers, the heart of endpoints. What makes tiny machine learning? The key point of our course.